Right, hello everyone. Welcome to today's Resilience of Autonomous Systems seminar. It is my great delight to introduce Jeff Kramer, who will give the talk today. And Jeff is Professor of Computing at Imperial College London, where he's been carrying out research work primarily concerned with software engineering, with a particular emphasis on evolving software architectures and behavior analysis, and the use of models in requirements elaboration and self-organizing adaptive software systems. As an early result of his research, he co-developed the Darwin language for evolving distributed architectures. And in more recent work, he has co-authored the widely used three-layer model for self-adaptive systems, which deals with the major challenge of performing requirements analysis at runtime. Jeff has been involved also in major conferences and journals, and in particular as program co-chair of ICSI in Los Angeles in 1999, as general co-chair of ICSI 2010 in Cape Town, and he has been the editor-in-chief of IEEE Transactions in Software Engineering between 2006 and 2010. He has been awarded a wide number of prizes, including the 2005 ACM SIGSOFT Outstanding Research Award, also the 2011 ACM SIGSOFT Distinguished Service Award. He is a fellow of the Royal Academy of Engineering. He is a fellow of the ACM and a member of Academia Europaea. His talk today will be on resilience through adaptation, the challenge of change, and I'm very much looking forward to listening to the talk, Jeff.
Thanks very much, Radu. I appreciate that introduction, and I'm going to try to at least go through some of the work that we've been doing over quite a long career in this kind of area. I should say that I'm happy to take questions along the time if people wish to interrupt. If interruptions get too much, then I'll try and close things down a bit. But on the whole, I'm quite happy to take questions, especially in Zoom lectures. I found them a little bit distancing, and so you don't get the kind of engagement with people that I actually really like in a talk. So yeah, we're talking about resilience through adaptation. Some of you may have heard bits and pieces of this before, but hopefully there will be something new for everyone. So challenge of change. Change is an area that is inevitable in all kinds of systems. I mean, there is no way that we can actually fully understand complex systems. There are assumptions that we have to make, and the best thing about this is to make these assumptions explicit. And these assumptions we have to include in our models, because the models are always approximations of the real world. They're abstractions, and therefore inevitably will be subject to change as we discover more when the system is actually being used and run. So our models are always, let's say, not fully correct. They always have uncertainties and approximations in them. And the system itself will include, therefore, the kind of behavior which will therefore be subject to some kind of change. And if we want to make these systems more resilient, what we really have to do is to try to actually adapt them. Now we can adapt systems offline, essentially the old style, which was very much to do maintenance. But I think what I'm more interested in is trying to detect particularly invalid assumptions that we've made about the environment, or just uncertainties, things we didn't know at all, and to try to provide some kind of adaptation. One of the things we do is we learn from failures. So each time something happens, hopefully we pick up more information, and this adds to ours. And I think the nice thing about this is that this actual information is cumulative, in the sense that as we gain more, we should be able to improve our system more, with the goal that as we know more and more, we can still maintain and try to achieve the goals that we have for this particular system. So this is the area that I'm going to be talking about, which hopefully is, of course, I think central to the kinds of things that Radu does in your resilience project, and hopefully of interest to a number of other people as well. So in dealing with the challenge of change, as I said, one of the things that's occurred that we mostly do, and we've been doing traditionally for many years, is basically dealing with software evolution. And this is the standard maintenance cycle. You know, we perform requirements analysis, we go through design, implementation, testing, and so on, and redeployment of the system. And all of this is done by essentially doing an offline update and then redeploying the system. At the other end, we have runtime software adaptation. This is an area which I think in the last perhaps 10, perhaps 15 years has grown of more and more interest. And the idea is to provide self-managed adaptation. In other words, some way in which the system itself is actually monitoring the world and then adapting to it and trying at the same time to achieve the goals that it needs to. So this is the area that we're most interested in. And to put this into a kind of phrase, is the challenge is to try to automate and perform online everything that we used to do over here offline in performing maintenance. So we're moving all of these activities all the way through with testing, implementation, design, all of this kind of things, trying to push this into an adaptation approach. And this, of course, is as I'm sure you all know, is very challenging. So if we look even at the self-managed adaptation world, I think there's a spectrum of approaches that one can do it. So there's the light end, I would have said, where self-adjustment is essentially of runtime parameters. There's very little reconfiguration of the system. It essentially runs. But what we do is we monitor the behavior, and we then basically look at improving the system by changing the parameters of that system, usually in response to degraded performance or trying to improve the performance and optimize it. And I know that, for instance, Carlo Ghezzi's done a lot of work in this area, and there are many others who work essentially in that end of the spectrum. The opposite end of the spectrum I call the full fat. This is the one that actually clogs up your arteries and you're in danger of heart attacks. This is where essentially you're changing functionality, performance, and all, and you're responding to unforeseen changes. In other words, you may have to reconfigure the system, the goals of the system may change, the capabilities, you're going to get failure, and particularly the most common is that the environment that you assumed existed does not actually satisfy all of the assumptions. In fact, there were unknowns and all the things that I talked about earlier. And one of the people who I know works at this end of things, for instance, is Betty Cheng in the States and her team of people. And there are people who work, I would have said, between these. So if you look at the work of Danny Waynes, for instance, I think he's somewhere in between where they are adjusting parameters, but also have some reconfiguration going on. And the kind of change is actually, it's expected, but exactly what happens is not in fact known. So this is, I think, the worlds between, and you'll also find, for instance, if you look at the work of David Garland and Bradley Schmuel, you'll see actually across the full spectrum, right, all the way from the sort of adaptive light, all the way to the full fat. So there's quite a lot of people working in this area. I've named a few, but there are many, many others, and I apologize if I've missed out your work. The kind of thing you can imagine is drones, which I think we all like to play with. We have to have something to play with. And drones is one of the things you'll see from very others. But the important point I want to make is that it's essential in all of this to be rigorous about your approach. If you're going to work with robots, and this is the kind of reactive world that we've been playing with to test out our ideas, you need to be rigorous about this. And I think this particularly came home in an earlier talk in the series from someone from NASA who was talking about the rover and the kinds of things that they had to do in terms of time schedules there. They are incredibly rigorous about how to make sure that these systems will work at the right time. Interestingly enough, they're not, as far as I gathered, doing adaptive work in the kinds of way that we're talking about it, not yet. And this is because they need to be absolutely sure that everything's going to work. And so they still are concentrating on that, and clearly very successfully. So you can envisage these kinds of applications in at least some of the stuff that I'm talking about. So to be rigorous, we need to be formal. And essentially what I'm going to describe is an approach, at least that we promote, which does actually deal with things very formally. So we have E, which is an assigned environment, assumed environment behavior. G are the goals of the system, the requirements goals. And I is the interface capabilities of the system that we're trying to create, called system, in this case, system X. And this encapsulates exactly how we try to achieve this. So here's our environment, which is in parallel composition with our system, with its interface. And the idea is that this together should satisfy our goal G. So this encapsulates our let's say, goals in life. In performing, in actual systems, then, you can, of course, get changes, as I said, most commonly in the environment, but you can also get changes in the goals, the mission that the system is trying to achieve. And you can also get failures, which means that you get changes in the interface. All of this can change, and what we're trying to achieve in an adaptation of X, such that we can still maintain this achievement of our goal G. So that kind of encapsulates what we're trying to do. People will ask and say, well, what happens if something happens outside of the system, which isn't detected by the interface, by the sensors and so on? What happens if you actually need to do more? Well, these are the things which, if they're not in some sense in the alphabet of what you're trying to do, you do need human, almost as certainly you need human intervention to actually do something. So most of what I talk about is constrained to work within, let's say, the alphabets and within the interface that you have available. So with that proviso, I'll try to describe how we try to do this. So for this to work, what we need is we need to be able to support models. And these models need to be formal to support the rigor. So this is models at runtime of the environment, of this interface, and the goals that we need to achieve. We also have to have some mechanism of creating the plan or controller X that's going to actually perform the functions of our system. We particularly favor synthesis, so we can actually, given these models, synthesize a plan or a controller, which then works on the environment to achieve G. And that's what you need in order to do this. Now, this doesn't work unless this is all embedded in an architecture with a runtime environment which can enact the changes that you need to have. So the combination of all of these together provides you with the support that you need in order to actually do what I would call self-managed adaptive change. So I'll pause here at the moment. If anyone has any burning questions, I'm happy to answer them. I don't see anything happening. So in the absence of anything, I'll carry on, but please feel free to stop me. So what I'm going to deal with is I'm going to talk a little bit about the architecture and the runtime environment that needs to actually be in existence to support all of this. Now, one of the things is that MAPE is actually one of the popular approaches. It provides you with the phases or actions that you need in sensing the managed system, the environment that's out there, you monitor it, you perform analysis on that, you then plan according to what the next step should be, and you execute this. And this is called the MAPE cycle, with a sometimes also MAPE-K, because this is the knowledge part of all the models and everything that you need to do this. However, I have to admit that I find this slightly inadequate, or at least misleading in a certain way. This is not really an architecture. What this is a feedback loop, which is actually completely appropriate and is, as I said, very widely adopted. But as an overall architecture, it does not give you the kinds of structure that you need. So I think what's missing from this is a way of structuring a system so that it provides you with this adaptation. And secondly, this does not deal with latency in the system. In other words, there are parts of the system which need to react very fast, and there are other parts which can be slower and react at a slower time scale. And so if you look at just the MAPE cycle, you might find this misleading if you think this is the architecture of your system. It is certainly going to be part of it, but I don't think it is the whole answer. So in 2007, Jeff McGee and I did some work basically looking at the work of Gat, who was a robotics expert, and he had proposed a 3-layer architecture for robotics. We essentially adopted and adapted this and proposed this as a 3-layer architecture for self-managed systems. So at the top layer, you've got your goals, the goal management, which is where you do your planning. There's another layer here, a separate layer, which has all of your plans in order to execute those, and also assembles all the components to perform the changes. And then at the lower layer are the actual execution. And this is where, in fact, most systems run. And you may, if you're still very much, let's say, in love with the MAPE cycle, you can think of this as almost having a MAPE cycle or a MAPE loop for each of these various levels. When anything happens at a particular layer, which is inadequate, for instance, if I haven't got the right plan and something else, then a plan request is sent to the higher layer, and you'll have a MAPE cycle, for instance, working here, taking that, analyzing it, planning it, and then injecting that plan down. So, as I said, you can think of this as that MAPE cycles at each of the different layers. So this provides us, I believe, with a layered separation of concerns. In other words, one can work at the different layers. You can use, hopefully mix and match different approaches for each of these, but allowing you to have the separation of concerns. The other thing, as it said, is it provides you with a latency at different levels. This is the layer at which we expect things to happen at a fast time scale. And as we move up, things can happen at a slower and slower time scale because they occur far less often. Besides the fact, for instance, that planning takes a lot more time than many of the actions that we expect to happen at the lower layer. So this is the 3-layer architecture that we proposed and that we've adopted and use for most of the work that we do. And what I'm going to describe is a bit more in a bit more detail, but I'm going to describe them using the approach that we used. It doesn't mean that's the only approach, the only way of, let's say, achieving what's at a particular layer, but this is the way that we went about it. So let's start at the lowest layer. This is the layer which does all of the execution and must also support dynamic configuration of the components. This is the layer that actually interacts with sensors and actuators with the environment. And in fact, if we had just this layer, one would have a system which would quite capably could run. All it needs is the various plan actions to be injected and to be told, when to do what. But this is the layer that does the actual execution, as I said, and interacts with the environment. So if we look at this particular layer in a bit more detail in the way that at least we went about it, we had done work for many years on dynamic configuration. And so we'd worked with components. These are self-contained components. They have a very well-defined interfaces or provides interface, which you can call, and requires interfaces which make calls to other components in order to achieve their function. So there are self-contained components which can be instantiated. So in this case, we've instantiated a go-to task. We've instantiated a hardware which interacts with the motors, and there's a sky camera. So these are three components which have been instantiated. And you can see these define the interfaces of those. This is a provided interface that can be called, and this is one that requires, for the go-to task to work, it needs to be connected to a motors and location. And this can be done simply by binding these components together to form a configuration. What's more, you can actually support dynamic configuration by instantiating other components, removing components, rebinding, and so on. So this provides you with the basic layer that we have. What happens is this combination executes plan action. So this is a plan action. It's an abstract plan action saying, I want to move from here to there, move to. And this performs all of that by interacting with these other components in a fast manner, doing all of the kind of continuous control that you may need, also doing things, automatic actions like collision avoidance and so on. So this is a combination where we move from a lower layer. I have a tendency to want to point to the screen, but I realize it doesn't help you very much if I do that. So I've tried to use a bigger cursor. So these are the kinds of things that are happening automatically by the software. And these are the kinds of plan actions that we're going to be synthesizing in the longer term, which I'll show you in a moment. So this is the lowest layer. And this is a simple demonstration, for instance, of the kinds of things that we've played with for a number of years. These are little robots which move around. You can see here it's doing collision avoidance with that box, and it's going here in order to have this particular ball removed by this control arm over here. So that's one of the things that we do. So that's the lowest layer. Now what it does is it reports status to the layer above. And what we do here is choose a particular plan to be executed that will assemble the components necessary for that plan and then execute the plan using these abstract plan actions that I've mentioned before. So let's have a look. This is, for instance, plan execution. You can see we use, in our particular case, we use what are called reactive plans, which are condition action rules. In other words, we say that if we're at location 1 and it's not loaded, then we can perform the pickup action. If we're at location 1 and we are loaded, then we should move to location 2, and so on. And this forms a graph of preconditions that can be satisfied, and these would be the actions that we need to execute in order to achieve our goal over here. So we want to be able to finally synthesize these kinds of reactive plans, and then what happens is it performs these plan actions. Now, in order to perform the plan actions, we need to assemble the components to do this. And this is done essentially by performing a mapping from plan actions to the provided services of these various tasks. So for instance, the plan action move to is actually means that we need a go-to task in our system in order to achieve this. And then what we do is we elaborate this using dependencies from the required interface to the provided in order to satisfy this. So I can show you this essentially by saying, if I have a move to task here, what I do is I want to do before component assembly, we do what I did before. I connect, I instantiate these components, and then I bind to them. As far as dynamic configuration is concerned, then, for instance, if the sky camera fails, then what I can do is I can instantiate a SLAM component and a webcam component and bind to those to try to perform the same task again. I see there's a question from Colin. Perhaps if you'd like to, I don't know if you'd like to ask that now, Colin, or.
Sure, Jeff. So I'm just interested, when you had the 3 layers in your architecture there, and you were talking about latency, I think that means there's some kind of temporal separation and an assumption that controllers actuators act fast, planning act slow. I wonder what that means in terms of a need for replanning comes in when we're halfway through something. So our plan says move from A to B, and I'm halfway to B when I realize something has to change. What do we do about this? Do we need to be looking at atomic things and saying that we have assumptions, or are there ways of dealing with that?
That's a very good question, actually, and not one that I have to say we've dealt with very well. The way that we envisage and the way that we've done this is that any, if I go back, if I can get back, well, if you go back, what you'll see is that we're monitoring all the time what's happening in the system, so that if something, for instance, during you're moving halfway along, you say, and something's happened, what happens is this needs to report that status to the level above. So the level above is then being told that I am unable, or something has happened to make me unable to achieve the action that you've told me. Now, in doing that, it's then up to the planner to say, that action is unachievable. Now, do I have an alternative plan action that I can achieve in this reactive plan? Is there some other precondition which is satisfied and I can do it? If not, is there an alternative plan sitting on my shelf which I can then use? And if that's not the case, then I have to replan. And so I go to the layer above to say, give me a new plan. So I hope that gives you some feeling as to the way it is. So even if it is interrupted, there is actually a mechanism and a way of essentially dealing with that, essentially by having the status reporting, not just at the beginning and the end of these actions, but if anything unexpected occurs.
Okay, so it's important to have a level of abstraction at that bottom level that enables you to know.
Absolutely, exactly. And it provides you with that kind of separation to allow these things to happen. Thanks for your question. That's very nice. Okay, so essentially what that does is that's the change management layer, where it has these plans. As I said, you can have pre-computed plans sitting on your shelf, which you may choose between them. And what it also does, this layer is the layer that we said assembles the components necessary to achieve the task, but also, if necessary, tells the system when to do dynamic configuration. So let's move to the top layer then, which is the goal management layer. And this is obviously the most difficult. As we move up, it becomes more and more challenging. And the particular way that we've approached to do this is to use what's called controller synthesis, plan synthesis. And it's based on the work of Pnueli and his colleagues, where you consider a plan essentially as a winning strategy between 2 players. So we have an environment which has all of our assumptions and so on built in it. And what it does, and what we also have, is the system that we're trying to synthesize. Now, they interact through an interface where we're getting input events from the environment, and we have control actions coming from the system. Now, in this 2-player game, they are trying to achieve a goal G. And what we're trying to do is to synthesize it in such a way that no matter what input events the environment throws at us in the alphabet of these input events, we will always be able to achieve the goal G. And so what we're trying to do is to synthesize X such that given E, and no matter the order of the events that it throws at us, we will still be able to achieve G. And this is the work. There's a very nice algorithm for safety properties, which they've done. And one can now do this kind of thing with some liveness, with constrained liveness, it's called GR1. So I'm going to show you now briefly just how we do it as in our particular approach to achieving this. So we use label transition systems, and we use our label transition system and that analyzer. What you do is you basically model the environment and all of the things that it can do and the actions that you can perform as controlled actions. And this can be a parallel composition of this complex environment. You then have a goal specification of all the properties, all the things that you wish to achieve as essentially in, as I said, linear temporal logic. And then from that, using model checking, what you do is you'll find that there's good behavior, but there are also some behaviors which will take you, may not be very visible, to this -1 state, which is an error state in our system. In other words, where the property is being violated and you actually need to avoid this. So what we need to do is to prune this particular graph to ensure that no matter what events occur from the environment, we can still achieve our goals. And from that, we then essentially generate a controller which has these kinds of actions: not aligned and grip open and pick up, then open gripper, and so on. I'll show you briefly how this is done. So for uncontrolled or environment inputs, you take your graph and you propagate backwards any your error state. This is to make the error state unreachable by the environment action. In other words, if the environment suddenly in this state did this input, we would be in our error state. So what we say is we're trying to prevent that from happening, and we just propagate back the error state to here. For control actions, what we do is we eliminate that control action as one of the options that the system can therefore do. So we eliminate that, and you eventually move back. Now, if you keep doing this back propagation, then what you end up with is a graph which has an achievable goal, and you will never go to the error state. You will never violate the system. If, however, there's no such graph, in other words, it becomes an empty graph, then it means that under those conditions, actually, there is no synthesizer, there's no system X with an adversarial environment which could achieve your goal. So this provides, I hope, some indication of how we achieve this. We then extract a plan by using what are called fluents. So we label each of the states with fluents, and these fluents describe what is true at that particular state. And then we use those fluents as the precondition for these particular control actions. So whatever's true in this state, we're allowed to perform this control action. If this input has happened and we're here, then this fluent describes the precondition for this control action, and so on. And that gives us our controller. So I hope that provides some input into that. So
may I ask a quick question, Jeff? So I was wondering if this approach is not going to be over-conservative in some scenarios, because if you consider that the environment can throw anything at you and you want to prevent that at all cost, then you'll avoid some actions that can bring you progress with the goals. And maybe that environment behavior is highly unlikely, so you might be prepared to take that little risk.
You're absolutely right. This is an extremely conservative approach, and you may, which is why I said this is the particular approach that we've adopted, but it's not necessarily the most practical. And exactly what you're saying is that if you wanted to, and if you put those assumptions very clearly and explicitly, you could put probabilities on these various arcs. And if you can then do a synthesis where you're saying any of those where the probability of that occurring is below whatever you want your threshold to be, you could eliminate those automatically, let's say, and then do your synthesis. And that would provide you, for instance, with an approach which perhaps is more realistic for your particular environment with your assumed probabilities. But I think, as I said, different approaches, but you're absolutely right. This is a very conservative approach. I'm also happy. I see there are a number of questions going on. I don't know if you want to do those now. Bashar, I can see his name's appearing.
There's a bit of discussion ongoing, but we can delay it until the
Okay,
end.
so shall I move on then?
Please do.
Okay, so that I hope gives you a description of the three-layer architecture, particularly with its separation of concerns, and as you can say, an interface between those when you need to get a new plan, you get a plan request, and then hopefully do synthesis and push that plan down, which then would do its assembly and so on. And exactly as Colin was also saying, there is this notion that these actions are happening on a fast time scale. These are the ones that you need, actually, perhaps even continuous control, and these are happening at a slower time scale. So, for instance, here is another little example just to show you that adaptation, for instance, may require components reselection, as I showed you before with failure. What's happening here is that this robot is trying to find the robot arm, but it's not succeeding too well, and it's using a particular zigzag pattern, which is the plan action, to try to find it. So this is going to use an alternative plan selection. So after a certain time, it times out, takes another plan off the shelf, and then adopts a circular plan, which, as you'll see, since we were playing around with this, and I wouldn't show you demonstrations which failed, as you can see, it eventually finds the robot arm. If that hadn't worked, then we may have to, of course, gone for replanning. So in actually creating the systems that we've been playing with, what we did, as I said, was work with label transition systems to model our domain, plan, control, synthesis, as I described. We have a plan interpreter, which works in the middle layer, and an assembler, which assembles all of the components and instantiates them and binds them together. And then at the lower layer, we used what was called a backbone interpreter. This was some work by a PhD student of ours called Andrew McVeigh, a very nice piece which allowed you to actually do the configuration and dynamic configuration using Java. And that's the layer which interacts with the environment via sensors and actuators. So this was our particular realization, and we published this in 2008. And I'm happy to say we even got a MIP award recently for that.
Jeff, may
I
ask a question?
Absolutely.
Do you think it within that, I can see a situation where we realize at runtime that there is something more fundamental than this needs to change. So for example, your little example you showed there, it needs a different robot with a new capability. So where do you think, I mean, what would we call that? Is that redesign? And what does that live outside of this circuit that we have here? Or is it above it as a fourth layer? What's your thought on that? Well,
my feeling is that, as I said, this is all working within, one could think of, I wouldn't say a closed world, but certainly a world which is constrained by its alphabet, its interface, and all the other things. So when you get to this top layer here, what you're saying is that whatever is going on at this lower layer, it's not achieving what I want, and I cannot create a plan. In other words, if I try to do synthesis, it will fail. And this is the point at which we really have to ask someone to intervene. So there is a point of what I'd call failure of this, which actually prompts intervention. Now, at what stage you might want to do that? Earlier than going through all of this, or you may even want to be monitoring, having somebody, for instance, monitoring the status so that they can intervene earlier and so on. That, I think, is up to design. But it does, at least as far as I can see, I don't know of any other way, but actually human intervention is when this is prompted, when this needs to be prompted.
Okay.
I mean, you could You could even think of it as a fourth layer with a human being on it, I suppose, which is then being requested.
Yeah.
Is that answer?
Yeah, that's great. Thank you.
Okay, I'll just try and step through this. So that's been reasonably successful, as I said, but we're still, of course, trying to add new things to this. So one of the things is, for instance, you need to, if you get unexpected domain behavior, which is, as I said, one of the most common things where something happens and you didn't expect it, or it's not in your model, certainly didn't expect this to happen, we need to generate revised plans. But first of all, we need to actually revise our model. So what we do is we did some work in 2013, which essentially logged the behavior of the system and then used inferences on these execution traces to update the model. What it did was we used a probabilistic rule learning system, which hypothesizes what rules would satisfy this new behavior and eliminate any bad behavior. But it does this in a probabilistic way by ranking these as to the most likely explanation for that particular behavior. We then would select, and we use somebody to select these, but you could select the one with the most that is most likely, to modify the domain model, perform synthesis, plan synthesis, and then use that. And this provided a way of modifying the behavior and modifying the model. And also, since our rules are actually the logical rules, they are reasonably readable and can actually provide feedback to the user. So this was one of the pieces which I think we worked on. And I think there's a lot more that can be done in this area. And I'm sorry that we didn't do more on this. What we also realized as a result of doing that was that we needed to make more explicit what I think is the K part. Like in MAPE-K, there's a K part to this, which is all of the stuff to do with the models that you need. So you need to have all these models at runtime. They need to be available. And we had somehow embedded them in here. So we actually realized that we needed to make this more explicit to people so that you could actually perform your logging, perform inference, and then use this, this K part, the knowledge part, to have your models at runtime. And of course, what it then allows you to do is reasoning at runtime, which is the essential aspect of having these available, so that you can do that and exploit those. And you need tools and everything to do that, of course. One of the other questions that you have to be able to answer is, how can I safely change a controller at runtime? In other words, if you're going to perform dynamic configuration and change plans, move from one plan, the old plan, to the new plan, you need to be able to do this in a safe way. We had used an approach which we, from the 1990s actually, called quiescence, and then later some technique called tranquility. But more recently, in 2016, what we used is an approach called dynamic controller update, which goes through a process of allowing you to literally swap controllers and move through a transient period from the old controller to the new controller where you're satisfying a new specification. So this is actually some work. This is a diagram from some drone experiments that my colleague Sebastian Uchitel has been having a lovely time going off to Patagonia on a regular basis. So this is, for instance, a drone which was operating here, doing the red part over here, and it's called upon to perform a new goal. And so what happens is you hot swap the old one with this new specification. It goes through it stops the old specification, goes through a transition period with satisfying certain of the properties, and then starts the new controller with new reconfiguration and performs this blue part over here, and then eventually goes back to land. So this was some work which I think satisfied one of the thorny problems of how does one perform dynamic controller updates in a way which satisfies certain properties. What we found, though, is that these properties do need to be specified by a human being. They're very difficult to have those completely synthesized. This made us also realize, in thinking about this, that one of the things that you're actually doing in the end, in fact, is that you're performing requirements engineering at runtime. This is clearly, I would have said, not only challenging, but in many cases is going to be impossible. So without human intervention. So I think this is actually the area which I would say now is one that we need to concentrate on. Now, we've done some work on requirements engineering and requirements elaboration. For instance, if you think of this as an operational requirement specification, one can use inductive ILP, inductive logic programming, with some more positive and negative examples, and it will generate then a explanation, in other words, a better specification, which satisfies the positive and eliminates the negative. And we used an approach which, by using goal and model checking, basically used counterexamples to provide the negative examples and positive examples, in other words, witnesses, to feed into our ILP and extend it. So this is performing, in some sense, requirements elaboration, but we did this, of course, all offline rather than online. And we're going to have to try to do some of this work, I think, online as much as we can. So my question is really, to what extent can we use these kinds of techniques and tools at runtime to actually do requirements engineering? Runtime analysis could be triggered, for instance, by the detection of a violation of an assumption. So you need some good detection techniques, and we could actually trigger it. And then resolution, as I've shown you before, requires changing invalid assumptions or violated goals and changing your model. And one of the things that we've been looking at just more recently is to combine this runtime violation detection with ILP learning and controller synthesis in an iterative process. So what I'm going to do now is just show you briefly, to give you a taste of how we envisage this could be done. So if I have a controller C that achieves a goal under some environment assumptions A, so, and I've written it like this, so we're achieving G with these assumptions, and this is the controller. If we get a violation of these assumptions, then what do we do? Well, what we can use is we can use our learner to produce a weaker assumption, which is still satisfied even by this new violation. But now we don't know whether it will actually achieve our goal. So we try using our synthesizer with this new assumption. If it can produce a new controller, which can still satisfy this goal, then we're done. Then we have success. In other words, what's happened is we've weakened our assumptions. It satisfies what the environment does, and we can still have a controller. If that's not possible and there's no controller which is realizable under these circumstances, then we have possibilities. We can try to find a different assumption, which is, let's say, weaker than A, but stronger than A dashed. In other words, it sits in between those two. And then we can try again to do controller synthesis. However, or let's say alternatively, we can try to find a new acceptable goal, in other words, which isn't as stringent, and using that same, let's say, weaker assumptions, try to synthesize it. And this is essentially playing around with your goals and your assumptions to try to find a way of achieving things under the current conditions. But this is still work in progress. As I said, I'm doing this with Dalal Al-Roja at Imperial and also Sebastian Uchitel. And unfortunately, I thought we were doing quite well until the virus hit us, and research work seems to have become, at least in my circumstances, very difficult to do anything. So what I'd like to sort of end with is really saying that the elaborated 3-layer model, I think, has held us in good stead for doing the self-managed adaptation. It provides us with the kinds of separation of concerns, with the right kinds of separation with respect to latency, support for all of these, at least in outline. And then one can also replace various parts of this or experiment with this and hopefully use other people's approaches as well to improve what we do and to build systems which actually achieve this. The real challenge is doing this, of course, the RE end of things. So for resilience, as I said, I think we need to automate and perform online, or conventionally performed offline. But I would like to emphasize that we need to be aware that this may require, as I think Colin was mentioning, human intervention to guide, add information, and make judgment. I think this is crucial. Machines, as we know, are good for reckoning and for performing these things. They do them fast. Humans have judgment, deliberative thought, ethical commitment, responsible action, and so on. So I think that one needs to be very careful, and I really applaud the project that Radu leads in, I think, combining, and I know that this is close to Bishar's heart as well, in combining all sorts of people from, you know, all different backgrounds, whether it's legal aspects, whether it's psychologists, but also people who are grounded in ethics to look at these kinds of systems. Because in automation, basically, when it comes down to it, humans care and machines don't. So they will carry on and do things, and there are many cases where you need humans to intervene. Finally, then, I just want to say that in doing all of this work, I've worked with many people. One of the joys, I think, of doing research, of course, is all of the various people that you come in contact with and work with. And I can only encourage researchers to work as teams, but if we're going to solve the difficult problem, you're not going to be able to do this alone. So if you are still listening, thank you very much. And I'll try and answer any questions that you might have.
Thank you very much, Jeff. So we can move to the questions, and there are already a few in the chat. Christina, would you like to ask your question first, if you are online?
Yes, thank you for the very interesting talk. I have written a question in the chat about what about system of system adaptation. So when you have a system that interacts with other systems to perform or to achieve a goal, and can this 3-layer architecture that's been proposed work with this kind of system when you want to adapt not only the individual systems, but also the system as a whole, and you have different individual goals and team goals, like in a fleet of robots, for instance?
Thank you. Thanks for the question. Yes, the way that we've dealt with it up to now is to say that for each system, if it's system of systems, each system treats its subsystems, if one treats it as a hierarchy, as its environment. So in other words, that the subsystem can, of course, interact and throw things at you that the higher level system has to then cope with. It's more challenging if this is not centralized, of course. So the notion of treating this, for instance, as peers in a let's say with multiple systems is more challenging because, again, we have so far at least treated all of the other systems as part of the environment. Now, in making sure that that decentralized group actually achieves some ultimate overall goal, one has to be able to argue that, we've not constructed anything which does that in a completely decentralized fashion. But certainly, at least in the system of systems and the other way, we've tended to use these, each of them being a 3-layer architecture, but we've tended to do this as a hierarchy, or and treating, as I said, the other systems as subsystems. I'm not sure if that answers all your questions, all that you did.
Yes, thank you. I have a related question with what happens when the goals for the individual systems are contradicting with the team goals. So, for instance, a robot that being part of a team needs to move to pick up an object and leave it in another position, and its individual goal is do the task as soon as possible, but being sure that you don't run out of battery, for instance. This is a personal goal of the robot, so something like, I don't want to die, okay? But the team decides that this robot is the one that has to go to pick up the next object, because it's the one that is closest to the object. But it's running out of battery, so it has a kind of conflict. I am the best one to do this task, but I'm not a good candidate because I'm running out of battery, and I don't want to make my goals fail somehow. So how to deal with this kind of hierarchical goals?
I don't have any any straightforward answer. I mean, in looking at those kinds of things, as again, I can only think. It's not an area that we've dealt with directly, but I can only think that what we would have to have again is a centralized notion, where the goals, when the goals become, let's say, incompatible, in conflict, something has to be resolving that conflict, and that has to be done, at least in my mind, at this higher layer. So if there was a number of, let's say, subsystems, there would have to be a superior system which is sitting monitoring this and performing exactly the same kind of layered architecture, where if things come into conflict, you'd have to be able to detect it. I don't know whether this would work or whether this is the right way to do this, because in fact, in let's say resolving conflicting goals, there are often, as you say, things which they both need to achieve. But you know, what's the best approach? I don't really know. So I'm afraid I don't have a very clear answer for you.
Okay, thank you very much. Thank you very much for that.
You're welcome.
I find this discussion very interesting because it makes me think whether we are not overcomplicating the problem that we are trying to solve, in the sense that even a team of humans would have difficulties coping with the situation in which someone is assigned a task, maybe agrees to carry out the task, but then does not. So those are very difficult scenarios that maybe are infrequent, but of course we need to take them into account.
Well, I think, yeah, this is actually exactly what you're saying. This is the kind of situation where what you're doing is, it needs to be negotiation, there needs to be something, and resolution out of this. As I was hinting at, in some senses, that having something centralized do this and then say, okay, this is the way we're going to do it, is much easier than doing this in a consensus form. But there are, I know, quite a few AI systems which have done negotiations and so on in these kinds of environments. But this is not my area of work. It's not my area of expertise, I have to admit.
Colin, you had another question?
Thanks, Jeff. I mean, this is fascinating. I could ask questions all day, but I realise others want to as well. You talked about runtime resolution. And about the violation of assumptions. I wondered if you'd done anything about the nature of the assumptions. So how it changes your thinking if these are structural model violations, or their parameter violations on thresholds, or capability assumptions of the robot versus stuff in the environment. So I wondered if there's anything done that says, you know, not all assumptions are created equal.
Oh, I completely agree. I think not all assumptions are created equally, and the implications of these, you know, violated assumptions are also don't have necessarily. So as you say, a sort of some things are just essentially a parameter change in what's happening, and others require a complete, you know, reconfiguration of the system or completely new pieces of software in order to cope with it. In terms of actually categorizing these into these different levels, let's say, we've done no such work in terms of trying to do this. It's actually an interesting area that one could try to do that, so that one could say, you know, is this an assumption I would like to make and I can make easily because I can correct it easily, or is this going to be a major, you know, a major assumption, in which case I need to assess how risky this assumption is, in which case I need to then perhaps do some more work in terms of trying to mitigate it and so on.
Yes,
but no, I've done no work in that.
Yeah, no, because I wonder if even at a basic level, one could look at, because we've got a fixed alphabet and because we've got a semantics that are laid out, one could argue a priori that certain assumptions can be captured by the modeling and the reasoning that we allow, whereas we would know in advance that certain assumption violations would just invalidate everything.
Yes. Yes, you could almost categorize some as being, let's say, catastrophic and others being minor.
Yeah, back to the drawing board. Yeah, absolutely.
Yeah, but we've not done anything like that.
Okay, thanks, Jeff.
Right, so I am going to read a question from Alex Lascaridis, who cannot access the microphone. Alex is asking...
Actually, I can now. I've changed my mouse. There was something wrong.
Please do ask the question then.
Okay, so I'll just ask it. So, you know, the set of possibilities in the hypothesis space in which you're planning is essentially defined by your vocabulary of predicate symbols, yeah? So as far as I can see, you're assuming a fixed vocabulary of predicate symbols, and the assumptions are really about rules that are expressible in those predicate symbols, and you can
in the way that we've done it. Yes.
Yeah, so I'm wondering how you might refine your algorithms to handle a situation where your observations essentially show you've got a missing concept. There's something you're unaware of that you know, your hypothesis space is too small. Now you can imagine that happening if you actually have only partial information about the goal, but once you've performed an action, you observe a reward, right? There's some, you know, a numeric reward, it's good or bad. And you find in two instances of an atomic state where you do something, in fact, the same thing, you get a different reward, yeah? So you could imagine, for example, I'm a robot dog. I love, you know, my goal in life is to be petted and lots of attention. And so when I'm in the vicinity of somebody, I go and I wag my tail and I get lots of attention. But then I do it one time and it's just a complete disaster. And I sort of learn about dog catchers, and I didn't know about dog catchers, you know, they're to be avoided, right? How would you refine your sort of systems to deal with that kind of issue? And don't you think human intervention is actually critical for dealing with a situation where there is a logical inconsistency? It's like your hypothesis space, you observe it's too small and something's got to be refined. A human's got to tell you how to refine it, right?
Yeah, no, you're absolutely right. I think the world that we've lived in, as I said, is this closed, at least fixed alphabet. And there may be actions in the environment which are, let's say, seen only indirectly, for instance. And there may be hypotheses that you have where a finer grain will give you much more information and give you exactly the kind of thing to have.
Exactly.
We have no mechanism for dealing with that automatically. I have no suggestion. This is an area where I really feel, I mean, I'm not the person who works in the sort of AI area. I'm not the person who could do this. But I think there are people, and this is exactly where, if we have, at least in my, if we have this structure, you know, in existence, which does these various things, then we can start to tease out all of these extra things exactly as you described, and look for the techniques that would deal with it. But at the moment, I have no other suggestion but to actually say somebody needs to be involved in this, because you know, we're not succeeding, let's say, or our plan sometimes fails. Therefore, our goal is not correctly specified if the same state, you know, achieves both good and bad. So this is really not, you know, not something that I could either that we've done or that I could do. But the only suggestion, the only way we've dealt with it up to now is by humans intervening and then saying we need to elaborate our model. You know, we need to include more, you know, more rewards, or we need to include more states, or we need to include more sensors, or whatever it is.
And of course, human, if you're dealing with uncertainty, the human will. It's about, you know, it's a finely tuned human judgment on whether you should add another chance node, essentially, and models its probability distributions and dependencies, or whether you should just pack it into the noise of what you've got.
But what's I think crucially important also is to be able to give feedback to the user about what's gone on. So you need to be able to say that in the model, this is the point at which I'm not succeeding. This is where it seems to be failing, which is why I think that having rules and having these explicit forms that in some sense the user can read, then allows the user to say, okay, it looks like, you know, I need to be able to specify more here, or this is the actual state which needs more, let's say, needs distinguishing between some hidden variable which says this is good and this part's bad, and therefore I need to elaborate that. So I think it's crucial that in all of these systems, we are also providing feedback back to the user to say what's going on, and so that they can watch and so on. So I believe that we can try to do this automatically. And I believe in tools providing us with suggestions, you know, about this might be a good way to do it and so on. Even to the extent, for instance, when they come up with a particular plan or a particular assumption, is to be able to say, that's a reasonable assumption. That assumption is not reasonable. So I absolutely understand that, but I think we need to play with these systems more in order to understand what we can do.
Right. Bashar and then Risa.
Yeah, I mean, so, Jeff, this is really fascinating discussion. I mean, just to follow up on what everyone's saying, Alex and Christina and Colin's last model, which is about modeling. I think there is a role. There is a role for even more modeling and using multiple models and reasoning across multiple models. So, for example, we could, through good design, decide that we might have, if we're, let's say, working in security, also have an asset model and a threat model in addition to the goal model. And that would allow us, for example, to understand the scope of the threats and to understand what it is that we're protecting. If we have more things to protect, we add them to the asset model. If we have new threats, we can add them to the threats model. The key challenge is to reason across multiple models and to understand that reasoning. And we can do that with good engineering. So I think, in a sense, your framework still stands by having good, solid reasoning and you know, feedback loops and architectures and so on. So long as we understand that it's not just the goal model that's going to drive the reasoning, there are other models. And similarly, for example, if we need more resources, then we can have a resource model and understand who owns those resources, and maybe have a stakeholder model to understand if we need to delegate authority. Then a la Morris Lohman, we delegate authority to the person who is authorized to do that and who has the resources to do a particular function. So there's lots of stuff we can do in engineering that allows more smooth adaptation. But the key is that we should be able to reason about this extended vocabulary that is provided by having more models.
Yeah, I agree with you completely. I think that there's no doubt that as one goes into a richer environment, so you need more and more of these kinds of models. And in fact, in terms of even selecting which plan you're going to use in order to achieve something, it may then be that you then put in resource constraints, or you put in security things and so on, so that the notion of choosing something, and using something else to decide which of the particular ones. And one can get you can go into sort of this kind of, Pareto kind of optimization or whatever, if you want to achieve multiple objectives and all this. So I think that you're quite right. In ours, being very much a sort of engineer and building these kinds of things, I was interested in, getting the sort of groundwork, getting the basic parts right. But in terms of as you go wider and you need to do exactly the kinds of things that you're talking about, absolutely, you need more and more of these models. Integrating them is pretty challenging, as we know from the viewpoints exactly. But yes, but yeah, absolutely, I agree with you. Thanks, Michelle.
Oh, it's I think the questions are becoming more and more difficult. So, question
more and more that I can't answer. Yes.
A question from Lisselle, who had to leave. Is there any part of the synthesis system that can provide an explanation when a solution is not found to provide insights to the user?
I don't know is the answer. Most of the synthesis work was done by Sebastian Uchitel and his colleagues in Argentina, who work quite a lot with the synthesis algorithm. So I don't know about the feedback. So when it comes back and says no plan, I don't know what kind of feedback is possible.
Mm. Right. So yeah, Colin had a comment, I suppose, more than anything else.
Yeah, I think he's following on a little bit from what Bashar said, is that we was talking about different models, and I think it's different languages. Done some work recently with AI, and often people will talk about interpretable AI and give an explanation that would still mean nothing to vast audiences. I remember reading a medical paper on AI where they showed me some pictures and this said, this explains retinal diagnoses. And I looked at the pictures and I thought, not to me, it doesn't. I think it's in talking about what is a suitable language. So obviously we love formal languages and logics, but often these are just so hard to talk about goals. And when we bring them up to that top level where we have non-experts setting goals for a system, I don't know what you feel about how we make that interface jump into describing systems that others will understand.
As you say, I think it's getting to the stage where I have to actually just reflect the question back at you. What would you suggest?
Can I tell you about 3 years' time, Jeff?
Yeah, I mean, these are all, that's why I think the area is so rich, actually, because for me, it encapsulates so many different aspects to do with how we're trying to build systems. Even in the limited adaptation that you provide, but all the way through, it raises all sorts of challenges. And that's why I think it's great from a social point of view and all of the sort of, economic or whatever kind of things, but all the kinds of user interaction. There's an AI, aspect to it as well, which can be integrated. I think that putting all of these, different techniques that we have with model checking and, synthesis and AI. I mean, we haven't even talked about the sort of machine learning, the statistical machine learning that's, the most popular part of it where, you know, you're training, you know, if you get enough of these two, you know, enough cases, you can actually train to do this. And I'm sure there's a part of this which, you know, in other words, that would be a useful tool, though it violates exactly the thing that you're talking about in most cases by being totally unexplainable as to what the hell it's doing.
I think the slight caveat I put on all of that is that we have shown that very simple models and very simple controllers work surprisingly well in real world systems. I think that's the truth. Is, you know, for many decades now, we have had simple controllers that work very, very well. So although we can talk about these very, very difficult cases, we still have things that work well a lot of the time. Yeah.
Oh yeah, yeah. No. We're succeeding, but I think adaptation and dynamic adaptation, you know, is hard. But if it was easy,
then we'd be out of a job.
Yes,
right.
Exactly.
Right. I think I will suggest that we finish on this positive note. Well, yeah, just said we are succeeding. So thank you again so much, Jeff. For
You're very welcome. Thanks for the opportunity. Thanks a lot, and nice to see you guys.
Thanks to all the participants for asking questions, and I'm looking forward to seeing you again at our next seminar in 2 weeks' time.
Good.
Bye, everyone.
Thanks very much, Radha. Thanks, everyone. Bye.